Welcome to example number 2 for the rational functions. Let's take a look at what I've got here. So if I graph that function, I get something that looks about like that. You see I've got a loop up here, I've got a loop down here and there. I need to know that these vertical lines probably don't exist. The calculator's just filling in the dots. So those are probably asymptotes. Good. All right, well, the first thing I need to do is factor top and bottom. That obviously is the difference of two squares, x plus 2, x minus 2. And, you know, there is an easy way to do the top, which is look at, I'm just going to plug in just the top function. And then I will calculate, I'll just get it to calculate the zeros for me. Yep. 1 and negative 1/2. Well, negative 1/2 would be 2x plus 1, correct? If you set that equal to 0, you get negative 1/2. And the other one should be x minus 1, if I'm not mistaken. Good. And, you know, I could always just multiply these out to double check. Okay, so write the domain. X cannot equal plus or minus 2, right? Set the bottom equal to 0, and it can't be those numbers because that would make the entire, you'd be dividing the entire quantity by 0. Can't do that. Write the ordered pair for any removable discontinuities. Are there any matches here? None of the factors are repeated on top to bottom, so there are no holes. Write the equation for any vertical asymptotes. Well, that would be x equals 2 and x equals negative 2. I can verify that quickly with my graph. There we go. X equals 2 and negative 2. Looks good. All right. Write the equation for any other asymptotes. Well, again, I look, top heavy, bottom heavy match. These are a match, so I take the ratio 2/1. So the asymptote is going to be y equals 2. And let's take a quick peek here. Yeah, see that right there? Right along that line, right along the line 2, this has an asymptote. Describe the end behavior. So on the left-hand side, as x approaches negative infinity, the function will approach 2, and on the right-hand side, as x approaches positive infinity, the function will approach 2. Good. Compute the x-intercepts. Set the top equal to 1, equal to 0. So that's going to be when x is, let's see, when so that's negative 1/2 comma 0 and 1 comma 0. Good. And now let's verify that real quick. Snap to intersections. There's 1. There's negative 1/2. Good. Compute the y-intercept. When x is 0, y is 1/4. I just plug 0 in for x. I get negative 1 over negative 4, 1/4. And let's just take a quick peek here and make sure we got this right. Snap to intersections roots. There it is. 0, 1/4. Beauty. All right, so now I sketch the graph. You definitely need to use this as a guide. So here, whoops, x equals negative 2. This should really be a dotted line. Sorry. This should really be a dotted line, and then another dotted line down here at x equals 2. Notice that I'm labeling these asymptotes, and then over here at y equals 2, there's an asymptote, and I know that this loops like that, and then this loops like that from the picture, and then I have this looping like this with 3 intersection points, there, there, and there. You need to label the axis, so that's a 0, 1/4, 1, 0, negative 1/2, and 0. So there we have the second example. Good luck.